All right, we are on chapter 7, section 3, and we're going to talk about attractive forces and how they determine solubility of any given molecule. So I'm sure you've heard before the golden rule, right? Like dissolves like. That's the golden rule of solubility, right? And it's down here, like dissolves like. And the reason we say that is what's the like? The like is the similar properties of the molecule. So when we talk about properties and solubility, we're really talking about, is something polar or is something non-polar? So, you know, when you have your salad dressing, right? And you have your vinegar salad dressing, it's oil and vinegar, whichever one has that, you know, when you pull it off the shelf or out of your cabinet, you see that layer of oil on top and then kind of the watery vinegar, right, down at the bottom. Vinegar is mostly water. And what do you do before you put it on your salad? You shake it up, right? You shake it up and then it mixes, but only temporarily, right? Because you want to pour it on your salad very quickly after you've mixed it. And so we know that oil and water don't mix. So why? Well, water's polar, and guess what oil is? Oil's mostly non-polar. And so they don't mix. But if you were to make good old-fashioned Kool-Aid, right? The old-time Kool-Aid, not the new packs that are like sugar-free. But like if you're like me, I remember as a kid, you know, when you make the Kool-Aid, you get the Kool-Aid pack out, but then you also get the sugar bowl out, and then you have to scoop sugar and pour it into your pitcher and stir it. But the water would dissolve the sugar. So why? Why does water dissolve sugar? Because sugar, guess what, is polar. And so whenever you're talking about, is something going to be soluble, it's whether or not it has the same kind of polarity. So do we have polar substances, polar dissolves polar, or do we have a polar and a non-polar? And that means that they're not going to mix, right? And so the maximum amount that a substance can dissolve in a given amount of water at a given temperature defines your substance solubility. And so you can change solubility by changing temperature, right? If you've ever, you know, anybody who makes real homemade iced tea, right? They get the hot water and they get the tea bags and they steep the tea bags in the hot water. But the key is that you've got to put the sugar in while the water is still hot, because more sugar will go into solution if you do it while it's hot. Otherwise, if you put the sugar in while it's cold, it'll be gritty because not all the sugar goes into solution. So you can change it with temperature. But what we're really going to talk about today is whether things are polar or not and how to figure that out. And so molecules that have similar polarity are going to dissolve in one another because they have the same types of attractive forces. And so instead of just wanting to interact with water interacting with water and sugar interacting with sugar, the sugar and the water are now going to want to interact because they participate in similar attractive forces. And so you might be more familiar with the terms hydrophobic and hydrophilic in terms of polar and non-polar. They mean the same thing. So if something is hydrophilic, it loves water. And so another way to say that is polar. So hydrophobic, something that is hydrophobic, is non-polar. So hydrophobic is water-fearing, whereas hydrophilic is water-loving. So if it loves water, it'll be dissolved in water, and so that's polar. If it's hydrophobic means fear of water, and so that's non-polar. So they're going to have different physical properties, right? And so we really only use these terms when we talk about solubility, right? And so when we look at compounds, we have to be able to figure out, are they going to be soluble or not? Well, let's look at a couple of examples. So when we first look at nonpolar compounds are things like oils, right? And we talked about oils. Oils are attracted to each other through London forces or London dispersion forces. But how does water interact with substances? Well, water is polar, and water is going to interact through dipole-dipole interactions, hydrogen bonding, and ion dipole attractions. So these two are not the same. These two here are not the same forces. right? And so they're not going to interact with one another. They're very unlike each other. And so the attraction for water to water is going to be very high. And the attraction for oil to oil is going to be high, but water and oil won't be attracted to one another. So because oil and water don't share similar attractive forces, they're not soluble inside of one another. So that's kind of how you do that. So when we talk about oils, what I want you to kind of think about is what is an oil, right? So water, water, right? That's water. And we know that water has our partial negative charge over here, a partial positive here, and a partial positive here. So it's very polar. But when we look at our oils and fats, we do know that we have some groups that could participate in dipole-dipole interactions. But if you look at a fat, at an oil, this is technically an oil, not a fat. But what do you see here? These are our fatty acid tails, right? And these fatty acid tails, these are the part that are non-polar, and they're so big that they take over the properties of the molecule. So even though you have some oxygens over here that do give partial polarity to the molecule, it's not enough to make a difference. And so what ends up happening is this non-polar characteristic of fatty acids end up taking over the molecule. And so they are non-polar, and so they're not going to want to interact with water. Let's talk about some polar compounds. So remember we talked about sugar. And sugar, we know now our table sugar is sucrose, right? And sucrose is very polar. Remember, every time we've drawn all of these sugars, all the time we're like, okay, what carbon are we on? Is that hydrogen and hydroxyl? Hydrogen, hydroxyl, hydroxyl, hydrogen. Well, all those hydroxyl groups, guess what? They can participate in hydrogen bonding and dipole-dipole interactions. And so they're very polar. So if you look at all the different hydroxyl groups that are on one particular sugar molecule, right? This is sucrose. So we look at each and every one of these. They can all participate in hydrogen bonding. The other oxygens can participate in hydrogen bonding as well. So here and here, right? So these are super, super soluble because they participate in the same kind of bonding that water participates in with itself. So table sugar, even though it's organic, is something that's very soluble. And the other important thing about solubility is that you don't have all your polar things on one side of a molecule, right? You actually want all the polar things kind of throughout the entire molecule, because in order to be really soluble, water is going to have to basically cover your substance. And so the most effective way to do that is to have polar functional groups all over the molecule. So you want like an even distribution of polar functional groups to be soluble. Okay. All right, ionic compounds. We know ionic compounds are things like NaCl. So that's the example we have here, NaCl. How did you get NaCl? Well, we knew that Na was in column 1, so it's a +1. Cl is in column 7, so it's a -1. So we know that they're charged, and so that's why they're attracted to one another. We write them as neutral, because if you look at this entire salt molecule, this entire ionic substance, right, the overall charge would be 0. But the sodium, and if you pick out one individual sodium atom, it is going to be positive. If you pick out one individual chlorine atom, it is going to be negative. And so if you put salt into water, what happens? It's going to dissolve, right? And so if you think about it, if sodium and chlorine ions are charged, well, water is going to be very attracted to that, right? Even more attracted to that than it is to itself. And so the water molecules are going to orient around our individual atoms. So, right, sodium's positive, and we know that our, erase this. We know that our, if I can do a different color, oxygen here has that partial negative charge, and we know that each hydrogen has a partial positive charge. And so you can kind of do that, and you can kind of see that the negative charge is going to kind of surround the positive. Well, guess what? It's going to be the complete opposite with chlorine. Chlorine's negative, so those hydrogen atoms are going to orient to where they are basically surrounding the chlorine. And then the negatively charged oxygens will be pointing outwards, right? And so we call this hydration. When you surround something in water, that is going to be hydration. So we have hydrated sodium and chlorine ions here. Okay. So how can we make this work for us in medicine, right? Well, if we understand the interactions of substances, we can better design substances to function inside the human body. So about 85% of all the drugs that are given to patients orally have to go through the digestive tract. And so our digestive tract, all of the substances that you eat, once you chew it up, right, it's going to be really dissolved in liquid. So the drugs have to be soluble in water. But the unfortunate thing is that a lot of the new chemicals that are being discovered are actually insoluble. And so what we try to do is to alter the substance and make it partially polar, so that at whatever pH this drug is supposed to be functioning, we have a charged part of that molecule. And so that will help it to dissolve in the body. So how do we do that? A lot of times we add an amine group or a carboxylic acid group. And I'm going to show you that in just a second. But this is, remember, this is what I said, you need to know those functional groups. You need to know those functional groups, right? Okay, so here's our first example. So you probably know the nasal decongestant, pseudoephedrine, right? And a lot of times when you buy it, if you look in the box and you look at the ingredient, it'll say pseudoephedrine hydrochloride. Well, what is that hydrochloride? Well, if we react the pseudoephedrine with HCl, then it's going to add a proton to the amine group. And then that amine group is going to be charged, and therefore it's going to be soluble inside of water. So this is our basic structure here of our pseudoephedrine right here. This is pseudoephedrine. When we react it with hydrochloric acid, so right here, we're looking at this amine group. What's going to happen to this amine group? This amine group is going to pick up an additional hydrogen here. So, and this is a carbon, right? Because it doesn't end in anything, it has to be a carbon. So initially we only had one hydrogen bond to that nitrogen, and now we have two. So that nitrogen becomes, look at this nitrogen becomes positive. So now we have not just one group that can interact with water, but now we have two. And so that's going to really increase the solubility and our body's ability to take up the drug. So it'll make the drug more effective. All right, so that's kind of one or the other. You're soluble, you're not soluble. Well, there's some in-betweens. Fatty acids. Fatty acids are mostly hydrocarbons, but we know that they contain a carboxylic acid group. So this is our general carboxylic acid group. But if I wanted to change this into a fatty acid, all I would have to do is add a really long chain, right, of carbons. And so that's our R group. Our R group is this carbons that are covered in hydrogens, right? So even though we have this carboxylic acid group, these compounds behave a lot like this carboxylic group was absent. So it acts a lot like nonpolar alkanes. And the reason why is because the nonpolar part of the fatty acid, all of this here, is so much bigger than the polar part that's the carboxylic acid. And so the larger portion of the molecule is going to determine the overall character of the compound. And so it makes fatty acids behave like they are nonpolar. But really, they have two. They have a nonpolar region and they have a polar region. So this is our, let me write that down. Nonpolar is all of this. And then this here is polar. And so because it has these dual characteristics, we call them amphipathic. Amphipathic comes from the Greek, amphi meaning both and pathic meaning condition. So they have both nonpolar and polar portions of the molecule. So that's why we call them amphipathic. So soaps are an example of an amphipathic compound. They are fatty acids that have been converted to salts. What does that mean? Well, we had our fatty acid. Let me go back real quick. We had our fatty acid, right? So you have that carboxylic acid group where you have your carbon, you're double bonded to oxygen, that's your carbonyl, and then they call it an acid because we have our hydroxyl group right there. Well, what's different between a fatty acid and a soap is that we've taken the hydrogen off of that, not the carbonyl, not the oxygen on the carbonyl carbon, but this other one that has a single bond, right? And it was a hydrogen, but we're going to get rid of that hydrogen, and now it's going to be negatively charged, and it'll associate with a positively charged ion. And so we know a salt is a positive and a negatively charged ion. And so this is what we mean when we say that soaps are ionic, because they've been converted to a salt. Okay. All right, so the charge, right, on our carboxylate, now that it doesn't have a hydrogen, instead of calling it a carboxylic acid, we call it a carboxylate. It makes this molecule ionic. And so fatty acid salts have really long non-polar hydrocarbon tails, that's true, but they have extremely polar ionic heads. And so these are another example of amphipathic molecules, and it gives them some unique characteristics, right? Soap's not soluble in water because look at this chain, look at this insanely long chain. That's lots of non-polar hydrocarbons, right? And so these hydrocarbons are going to not want to be by the water, right? They're water fearing. So they're going to associate with one another through London dispersion forces. And so what ends up happening is that these tails all want to interact together, and the heads all interact with water. And so they interact with water mainly through ion dipole interactions. So this is an ion, right? So this oxygen right here carries a negative charge, and so then it would interact with the hydrogens on water. And so that would be a ion dipole interaction. So because the water is only going to interact with the ionic head and the tails are going to associate with each other, they're going to actually want to create a spherical structure that we call a micelle. So this is an example of a micelle. Do you see how the tails are all hanging out with each other, and then the head groups are all hanging out with water? And so you got to think about this kind of in 3 dimensions. It actually makes kind of a bubble where all the tails are facing inward and all the heads are where my fingers are, the outside of the bubble. So the outside of the bubble is exposed to water and the inside is not, okay? And so the polar heads form the shell of the micelle, and then the core of the micelle is those fatty acid tails. And so the micelles form because of the ion dipole and hydrogen bonding interactions between the head groups and the water molecules. And that's actually a stronger interaction between these head groups. This interaction here is stronger. Ooh. So this interaction right here is stronger than water interacting with water. Right? It's very strong. It's a very, very strong interaction. Okay. So, how does soap work, right? Well, we know that dirt, right, and grease and things like that are non-soluble, right? They're non-polar. And so if you have on your skin or in your clothes, whatever it is, a piece of dirt or a grease stain or whatever it is, right? If we put soapy water on that, what's going to happen is that non-polar dirt or grease is going to be attracted to the tail regions of the soap. And so if the tail regions associate with the dirt and grease, right, it forms the micelle around that particle of grease or dirt. And so because that surface of the micelle is covered with our ionic head groups, the entire micelle with the greasy dirt in the middle is going to be soluble in water. So you'll have all these, when this is what happens when you wash your clothes, right? You end up with all these tiny micelles, and you wash that down the drain. So all you have to do is get the stain off of the clothes, the soap will wrap around it in a micelle, and then you send it down the drain. And so the only way that that works is if you have an amphipathic molecule, where you have those nonpolar tails that can interact with the dirt, and then you have those polar head groups that can interact with the water and be soluble in the water. And so we call these amphipathic molecules like soap emulsifiers, because they allow a combination of nonpolar and polar compounds to be suspended in the same mixture. So technically the grease and the dirt's still non-soluble, but because it's wrapped inside of the micelle itself is soluble, and so we call it all soluble. So that's an emulsifier. So what you need to be able to do is to look at different molecules and determine which one's more soluble, right? And then to be able to support your answer with data. So let's look at some examples here. Predict which of the following compounds is more likely to be soluble in water and justify your answer. So take a second, look at the molecules, and think about which one you decide. Pause it until you have an answer. Okay, so your answer should have been vitamin C. Why is vitamin C more soluble than vitamin E? So remember our rule that water must surround a molecule to be soluble, right? If we think our molecule is soluble, water's got to completely surround it. So more soluble molecules will have more functional groups that are polar, and the groups are spread out. Okay, so if we look at the polar groups on vitamin C, what do we have? Oh my goodness, look at all of those hydroxyls. All of those hydroxyls are going to be able to participate in 2 hydrogen bondings each, right? Because, well, actually 3 hydrogen bondings each, because each one of these oxygens has 2 lone pairs on it, and we're bound to a hydrogen. So each of the lone pairs here and here, these can be acceptor sites, hydrogen bonding, acceptor sites, and each hydrogen can be a hydrogen bonding donor, right? So that's 3, 6, 9, 12. Already I have 12 sites that could interact with water. Then what else do I have? I have a carbonyl group. My carbonyl group can be a hydrogen bond acceptor, right? 1, 2, 3, 4 lone pairs, so that's 2 more. What else do I have? I have, remember your ether is ROR, so this is an ether. So right there we have an ether, and so that can actually participate in hydrogen bonding as well, so that's another 2. Do you see how they're all spread out? So vitamin C is going to be more soluble, right? Let's look at our other one. Let's look at vitamin D. What can participate in hydrogen bonding or dipole-dipole interactions or ion dipole interactions? Not much. Right here and right here. So we have a hydroxyl and we have an ether. That's it. So 4 hydrogen bondings maximum, and that's it. No, 5, because you got 3 here and you got 2 here. So 5. You don't have to be able to count them. For this and the others you do, like which we did in the last section you do, but for this you just have to kind of be able to look at them and say which one's more soluble and why. Okay. All right, so let's look at another one. Which one of the following compounds is likely to be more soluble in water? Justify your answer. Naproxen or beta-D glucose. Pause it. Think about your answer. So what you should have come up with is that beta-D glucose is more soluble. Why? Oh my goodness, look at all these hydroxyl groups. And we have another oxygen there. All of those can participate in interactions with water. When we look at our naproxen, we have 1, 2, 3. You only have 3. So it's not going to be as much. And you only have those soluble groups on either end of the molecule. You don't have anything in the middle. And so glucose is more spread out, and you have more atoms that can interact with water. All right. Let's go do our practice problems. Okay, so here are our practice problems. And we have to remember, I wrote this little note that we just said, right? To be soluble, water is going to have to surround the compound. And to surround the compound, it's got to have those interactions, those dipole-dipole, ion-dipole, or hydrogen bonding interactions. So more soluble molecules will have polar functional groups that are spread all over the molecule. So what we're going to do is we're going to look at some examples and try and determine. So it says, based on their polarity and attractive forces, predict whether the following compounds are soluble, insoluble, or form a micelle in water. So remind me before we start this, right? We just talked about soluble and insoluble. How about a micelle? What's a characteristic that something would have to be in order to be a micelle? Well, you would want something that's amphipathic. Amphipathic, oh my gosh, how do you even spell amphipathic? Oh, that's terrible. Let's see, ampha, A-M-P-H-I-P-A-T-H-I-C? I don't know, that's not right, but amphipathic. All right, A, heptane. So when you look at this, what you should see is, oh my gosh, that's all carbons and hydrogens. There are no polar molecules in here. So this is all non-polar. So if it's all non-polar, we got no polar functional groups, then it is insoluble. Okay, how about the acetate anion? Oh, it just said anion. That has a negative charge. Oh goodness, what could we say about that? We have a negative charge. And if you were to draw this molecule out, right, that would be CH3, C, it would be a double bond O and a negative, right? And so we definitely have things that can participate in interactions with water. And so this would be soluble, definitely soluble. Okay, lauryl alcohol found in shampoos and skin cleansers. I keep looking at this word amphipathic and it's so not right, but let's see if I can change that. A-M-P-A-T-H-I-C, amphipathic, something like that. Okay, anyway, sorry. All right, so lauryl alcohol found in shampoos and skin cleansers. Shampoo, you should be thinking soap, right? And so what we have here, look at this huge group. That is all non-polar. That's all a hydrocarbon, right? But what about the very end? This very end is polar. So this is an example of an amphipathic molecule because it's got part polar, part non-polar. So this would form, this would form a micelle. That would form a micelle. Okay, based on their polarity and attractive forces, predict, oh, that's for class, All right, predict whether each of the following compounds is likely to be more soluble in water. Justify your answer. All right, a fatty acid or a fatty acid salt. So whenever you hear the word salt, you should think a positive and a negative, because that's exactly what a salt is. And so if we just kind of really quickly draw out an example of a fatty acid, let's do that first. Okay, so then we have, right, our hydrocarbon tail. All right, so there's our example. This is a fatty acid. right? Fatty acids have to have that alcohol attached to the carbonyl carbon. What happens when we turn that into a salt? Well, everything's exactly the same, and you can pretend that's the same number of carbons attached there. I don't know if it is, but there's no hydrogen. So this is the salt. So this is a fatty acid salt. So which one is going to interact more with water? Well, right here we have this negative charge right there. And so this is going to interact with water more than this, because these are ion dipole interactions, whereas this would be hydrogen bonding. And we know ion dipole interactions are stronger. So your fatty acid salt would end up interacting more and be more soluble. Okay, B, KCl or CH3,3N. What is KCl? KCl is an ionic compound. An ionic compound is a type of a salt. So you have K plus and Cl minus, right? The ions inside of there are going to dissolve in water through, this is strong ion dipole interactions, right? How about CH3,3N? Well, that's going to interact. It is polar. I'll give you that. It's polar, right? So if I were to draw it, I would have a nitrogen, and then I would have two CH3 groups all around that nitrogen. So would it interact? Yes, it would interact, but it's not hydrogen bonding. You would have, because you have this lone pair on nitrogen, you would have a dipole interaction. And so what's going to be stronger is our ion dipole interaction versus our dipole-dipole interaction. All right, so that is it for section 3. Y'all have a great rest of your day.